and explain why it's not a wild goose chase. Okay. Are we on a same page? Should I start going over this lecture and discussing more aspects of modular arithmetic? Yes. All right. Perfect. Right. So what did we do last time? Last time. Oh, is the camera nice and in focus? Is this okay? Focus. Okay. Last time we got the following result. So we're dealing with modular arithmetic. So we're dealing with A mod M being equal to B, and then we were also dealing with congruences. Oh, you can't see. So this is like a function, right? You're sending A to its remainder after you write out its decomposition via the division algorithm. So here, A is equal to MD plus B. If this is true, if this relation is true with B between 0 less than or equal to B less than M, then we can write A mod M is equal to B. We're taking the remainder, chopping off the remainder. Okay, this is one notion that we've discussed. Another very closely related notion that we discussed is congruence, which is we say A is congruent to B mod M. Can someone remind me of the definition of congruence? M divides A minus B, exactly. M divides A minus B, perfect. Very happy to see it. Okay, so the point is that these two different ways of using mod, here this is a function, here this is what's called an equivalence relation, which we'll get to. They're actually very closely related. And we proved that with a theorem. We proved, well, I proved one direction of, but the other direction's easy. A is congruent to B mod M if and only if A mod M is equal to B mod M. In other words, being congruent to another number is equivalent to having the same remainder mod M. And I think that this is something that probably y'all were implicitly thinking about or using before we proved it, but now we've proven it and we can use it freely. So this is what our kind of the last thing that we were discussing last time was proving. Okay, so what I'm going to do now is prove some supplementary results. So these are pretty easy, a next pretty easy theorem. Should I do an example here with numbers? I mean, just to work out what things are looking like. Okay, I didn't really have an example in mind, but let's find one. Let's take M to be equal to 7, because then we can always use our intuition about days of the week. So someone tell me some numbers A and B, they're not ridiculous. Well, I suppose we have to, someone give me a number A. 15 is a good one. So A is equal to 15. And I'm gonna pick another number, 50. So first question, is 15 congruent to 50 mod M, mod 7, where here we have to use the definition of, we have to use this definition. So does 7 divide 15 minus 50? Yeah, I think it does, right? So 50 minus 15 is 35. So 15 minus 50 is negative 35. So 7 divides negative 35. This is true because negative 35 is equal to negative 5 times 7. Yeah, I was thinking that too. and I was getting really nervous. But no, everything I've done is correct. Okay, so we've checked on our own that A is congruent to B mod M. 15 is congruent to 50 mod M. We just used the definition. But now the question is, what are the remainders when I apply the division algorithm? Well, 15 is equal to 2 times 7 plus 1. So 15 mod 7 is equal to 1. And similarly, 50 is equal to 7 times 7 plus 1. So 50 mod 7 is equal to 1. So what I can kind of verify and check here is that here I picked two numbers that were congruent, mod 7, and I observe that their remainders are the same, or their moduli are the same. That's probably not the word I should use, even though that is the traditional archaic way of saying it. And I can do a very similar thing going the other way. If I pick two numbers with the same remainder, then it'll be pretty easy to see that they have to be congruent, right? Something like if I work in a slightly more generality, not with actual numbers, but if I pick two numbers that have remainder 2, so let's say I pick A is equal to n times 7 plus 2, and B is equal to j times 7 plus 2, right? Here's a way to produce two different numbers with the same remainder after you've divided by 7. My next question is, does 7 divide n times 7 plus 2 minus j times 7 plus 2? The answer is yeah, definitely, because 7's going, if I expand this out, I'm going to have an n times 7. The plus 2 here is going to cancel with the negative 2 here. So I just have n times 7 minus j times 7. Or 7 divides 7 times n minus j. It's obvious that 7 divides 7 times n minus j because 7 times n minus j can be written as 7 times n minus j. It's, right? It's obvious that 7 divides this because 7 appears as a factor. Do these examples help us kind of see what's going on with this theorem? I hope so. It is pretty nice, I agree. Okay, so now let's prove another kind of auxiliary theorem. Really, this should be a corollary. I'm going to call it a corollary. So let m be in Z greater than 0, and then let A be congruent to B mod M. Well, shoot, I phrased this wrong. Period. Then A is congruent to B mod M if and only if there exists a K such that A is equal to B plus Km. In other words, to state things in words, well, I mean, these are words, but the point is being congruent, A being congruent to B means they're different by some multiple of M. And this is kind of obvious because this is just like a direct translation of the definition, right? What does it mean for M to divide A minus B? So this is really just a tiny corollary, but let's prove this. Okay, so this is an if and only if statement. So that means I need to do what? Prove both ways, exactly. I'm going to prove both directions. So let's start by proving the implication direction. So we assume that A is congruent to B modulo M. what can we do here? Then M divides A minus B, and what is the definition of divides? So, so A minus B is equal to Km, right? Dividing means I can re-express this term as a multiple of M for some K. So A is equal to Km plus B. Great, we've proved one direction. That was easy. Okay, let's prove the other direction. Assume A is equal to B plus Km. Now what? Just go backwards, right, that's true. So maybe I could say, now A minus B is equal to B plus Km minus B is equal to Km, and M divides Km, so A is congruent to B modulo M. Right, very easy. Okay, but now we've attacked this notion of congruence from many directions and kind of rewritten it many times. And this is a very helpful thing to know. If A is congruent to B mod M, then I can rewrite A as B plus some multiple of M. They're off by some multiple of M, such that S dot T is such that. Yep. Okay, cool. We're making great progress. Any questions? Making up for my 10 minutes of indecision about whether to move the homework back. Okay, let's see. Yes, a very nice theorem that will help the question that we were asked. New theorem. If A is congruent to B modulo M, and, I'm gonna give it a shot. And, not bad. And C is congruent to D mod M, then we have the following results. A plus C is congruent to B plus D mod M. And it's okay, you can always do the this one. And what else? AC is congruent to BD mod M. Okay, let's prove this. Let's prove the first one. Proof. Since A is congruent to B mod M, and C is congruent to D mod M, is there any nice way that we have of rewriting? Oh, I'm sorry, the black is like really bleeding through here. Is this annoying? Should I get a new page, or are y'all good? Okay, cool. So what should I do now that if I am assuming that I have some congruences, what should I do next? rewrite it as m divides blank is exactly what I would do. And then I'm going to go one step further using the last theorem and say, actually, I now know that A is equal to B plus K1M, and similarly, C is equal to D plus K2M. This is pretty much exactly the same as M dividing A minus B and M dividing C minus D. I've just gone one step further. Okay, so now let's examine A plus C and B plus D. So A plus C is equal to B plus K1M plus D plus K2M, right? And then B plus D is just B plus D. So A plus C minus B plus D is equal to K1M plus K2M, which is equal to M times K1 plus K2. Is this divisible by M? Definitely. M divides M times some integer. Thus, M divides A plus C minus B plus D. So A plus C is congruent to B plus D mod M. Is this okay? Okay. Should I prove the multiplication one, or do y'all want to try that, or what? I don't know which sure you're referring to. Let's do it, why not? But you'll have to help me. Okay, let's show AC is congruent to BD mod M, which really means use my expressions for A and C, and then we'll examine. So let's show AC is congruent to BD. What we first do is we write AC is equal to B plus K1M times D plus K2M, right? These are my expressions that I get from knowing that A is congruent to B and C is congruent to D, right? And then this is going to be equal to, I use foiling, BD plus DK1M plus BK2M plus K1, K2, M squared. Do we agree? Now, AC minus BD is equal to, well, I just chop off the BD. So this is equal to DK1 M plus BK2M plus K1, K2, M squared. Question, does M divide this right-hand side? Definitely. M divides the right-hand side, and I could show it by factoring out an M. This whole thing is equal to dk1 plus bk2 plus k1, k2, m times m. Since m divides ac minus bd, we see AC is congruent to BD mod M. How are we feeling about this? Okay, so let me kind of give an example of what this does for us. This theorem, this question is different from the homework one, so I haven't exactly shown 42, but this does help at least, right? This helps us understand what's going on when we're manipulating multiplication and addition. So the idea is the following. Let's say that we're trying to compute 50 times 25 minus 18 times 23 mod 7. This theorem that we just proved essentially says that there are a huge number of compatibilities. It's saying at any point, we can replace any of these numbers by their remainder mod 7. So one way to solve this would be to literally compute this number, find out what 50 times 25 is, and subtract 18 times 23, and then look at the remainder mod 7. That's one way that we could go about this. But another way that we could go about this exact same problem is replace each of these numbers by their modulus, modulo 7. So what is the remainder of 50 mod 7? 1. So I could just replace this with a 1. This expression, mod 7, is the same thing as 1 times 25 minus 18 times 23 mod 7. Right? This rule tells me if I replace this rule right here, tells me I can replace A, well, yeah, right. Essentially, I can replace A with B, and I can keep C the same. This one replaces both, but you can replace them one at a time. So I probably also should have showed that AC is congruent to AD mod M. But that's just as easy as this sort of thing. Yeah. So I can replace this with its remainder. Similarly, I could replace 18 by its remainder. So this is the same as 1 times 25. What's the remainder of 18 modulo M? Yeah, 4. Minus 4 times 23 mod 7. And at any point, I could just actually calculate. I could compute what is 25 minus 4 times 23, and then find the modulus, and I'd get the right answer. I could do that here. Or I could keep simplifying. What's 25 mod 7? Also 4, right? So I could also just rewrite this as 1 times 4 minus 4 times 23 mod 7. Okay, what's okay, so I'm currently at 4 minus 4 times 23 mod 7. What is 23 mod 7? 2, right? So this is the same thing as 4 minus 4 times 2 mod 7. And this is the same thing as 4 minus 8 mod 7. But what is 8 mod 7? 1. So this is 4 minus 1 mod 7, which is 3. And someone who's feeling enthusiastic can go and check that 50 times 25 minus 18 times 23 actually has remainder 3 when divided by 7. So, so essentially what these theorems have bought us is they're saying, if you have a bunch of numbers and you're trying to understand some big collection modulo 7, you can just immediately start replacing any part in here. I can immediately replace 50 by 1. I can replace 18 by 4. I can replace 23 by 2. I can just go replace in any point and I won't change the answer. So is this a kind of cool way to understand what this theorem is telling us? Hey, I'm happy to hear that people are enjoying some of this math. That makes me happy. Okay, any questions on this? Good, I'm happy to hear all these things. Okay, why don't we try 42 now? Yeah, we will get into the Euclidean algorithm. So let's examine homework problem 42, just for fun. Let's see if I can do it, or if we can do it together. So A, B, C, M are integers with M greater than or equal to 2. C is greater than 0. A lot of conditions that they want. Okay, so A is congruent to B mod M, and we want to show that AC is congruent to BC mod MC. Okay. So what does it mean? What's a comfortable and fun thing that I can do if A is congruent to B mod M? Right, I can do M divides A minus B, or if I take that one step further, A is equal to B plus KM for some K in Z, right? So now what I should do is I should examine AC minus BC. So AC minus BC is equal to B plus Km times C minus BC, which is equal to BC plus KMC minus BC, which is equal to KMC. The question, is KMC divisible by MC? Since MC divides KMC, which is equal to AC minus BC, we see AC is congruent to BC mod MC. I feel like a poet. Oh, you can't see what I'm doing. There you go. That's not, I mean, now hopefully you believe me that this problem is not so terrible, but we just needed to do a couple of examples and do some more theorems before this becomes kind of a sort of natural. Is this okay? Does this help? Yes? No? Perfect. Yeah, I think really what makes all this stuff become much easier is every time you see a congruence, you can rewrite things like this. And then you just have to remember that the definition of congruence involves the difference being divisible. Once you just kind of use those two things over and over again, most of these problems kind of open up like a flower towards the sun. Shall we continue? Yes, we'll continue. Perfect. So what this lets us do is this lets us define addition and multiplication on the set Z mod MZ, which is, for our purposes, well, as a set, this is equal to 0, 1, 2, all the way up to m minus 1, right? So I can define addition in the following way. A plus m, and I'll write this plus m to let you know that I'm defining an addition on this set, not on the integers. A plus mb is equal to a plus b mod m. So I'm saying, well, we'll do examples. And similarly, a times b, where I put a little times underneath the m, this is equal to a times b mod m. So the idea is, over here, you're thinking of a and b as elements in the set from 0 to m minus 1. Then how to actually compute an addition is you remember that they're actually integers, you add them like integers, and then you take the remainder mod m. Similarly here, I'm defining a multiplication on these elements. How you multiply two elements in here is, first you remember that they're actually integers and that we can multiply in the integers. You multiply them as integers, and then you take the remainder. Is this a reasonable thing to write? Is this okay, what I've described here? This is really a definition. Cool, I'm happy it makes sense. Let's do some examples, I guess. I'll just, should we take a different module? Oh, I shouldn't have written this. So the little mini m is on purpose. This is a way of thinking about this object that comes from group theory, which we won't ever discuss. So I was wrong to, so maybe I'll just say this is unmotivated notation. This is correct and cool, but we won't talk about why it's correct and cool. This object right here really denotes this set and these operations with all the additions and stuff. What's this little m for? So what I'm really defining, like addition, how do I write this? How do I want to go about this? So addition plus is a map from Z cross Z to Z. Namely, plus takes the element A comma B and sends it to A plus B. So addition is something that we define on the set of integers, or on the set of reals, or on the set of complex numbers. The point is, I'm now defining a plus sub little m, which is going to map from the set from 0 up to m minus 1 cross the set from 0 up to m minus 1 to the set 0 up to m minus 1. Now, obviously, this operation cannot be the same as this operation because, for instance, m minus 1 plus m minus 1 is equal to 2m minus 2, and 2m minus 2 is not inside this set, right? Like, let's say I'm working mod 7. My point is, I can't add 6 plus 6 being 12 and have succeeded. 6 plus 6 equaling 12 is not a function from 0 to 6 cross 0 to 6 back to 0 to 6. M here is just a little notation that's telling me I need to modify my addition. And the way that I modify it is instead of just taking 12, I take 12 mod 7, which is equal to 5. Now I have produced a function from 0 to 6 cross 0 to 6 back to 0 to 6. That is what I'm trying to focus on with this notation. Right, so if you added two numbers and they ended up being larger than m, you can't, like, that wouldn't define a map from the cross product from 0 to m with 0 to m up, or m minus 1 to 0 to m minus 1. So you have to do something further. And the answer of what we do further is we take the remainder modulo m. And then we land back in the set that we wanted to. Cross product is a beautiful, beautiful thing that will never go away, ever. And the more math you do, the more important it becomes. Fun. Okay, so it turns out that there are a lot of properties that we're familiar with for addition and multiplication that hold. So for instance, dot m and plus m are associative. So in other words, this means a plus mb plus mc is equal to a plus m b plus mc. This is what associativity means for addition in this operation, right? And it's the same thing for multiplication. So a dot mb dot mc is equal to a dot mb dot mc. That's associativity. We also have commutativity. So this is a plus mb is equal to b plus ma, and a times mb is equal to b times ma. We have identity elements. So for instance, 0 plus ma is just equal to a, and similarly 1 times ma is equal to a. We have additive inverses. What is the additive inverse in the integers? Like, what's the additive inverse of 4? Negative 4. Very good. So an additive inverse is something that you add to get 0, right? So now let's do an example of additive inverse. Let's say I'm working mod 11. What is the additive inverse of 7? Namely, what's a number in between 0 and 10 that I can add to 7 and get 0? Yeah, exactly. 7 plus 4 is equal to 11, but 11 mod 7, or mod 11, is equal to 0. No. You're not at all an idiot. The thing to remember is we always are working with these sets between 0 and m. And the idea is -7 isn't wrong. You just have to translate what is -7 modulo 11. -7 mod 11 is what? Well, -7 is equal to -1 times 11 plus 4. So -7 isn't the wrong answer. Well, it's a little bit the wrong answer, but it's only the wrong answer because you have to translate using mod back into the set of remainders. You see? It's actually quite beautiful. Right. So -7 wasn't the wrong answer. It just needed to be taken the mod of because it's not inside our set between 0 and 10. That's very nice. So this says the additive inverse of A is m minus A. So A plus m minus A, well, this is equal to m mod m, which is equal to 0. So we have additive inverses. That's quite nice. And lastly, we have distributivity. So this is something like A dot m b plus m c is equal to A dot m b plus m A dot m c. The point that I want to emphasize, what time is it? Oh, we're almost out of time. The point, how do we prove these? I just listed these. Do we have to write those little m's? What's the answer? In a number theory class, you would not have to write the little m's because in a number theory class, it's very clear that you're always working modulo something. Here, I would say you have to at least make it clear to me that you understand that you're not using the addition of the integers, but rather that you're using this new custom addition on the remainders modulo m. Like you know, it's important to distinguish between the plus on the integers and the plus m on this set. So I'm not saying that I'd immediately take points off, but you got to be clear about it. Okay, how do we prove these? Well, we prove all of these things by remembering that we defined plus m and times m by plus and times modulo m. So for instance, if I wanted to show commutativity, I would remember that addition on the integers is commutative. So let's prove a plus m b is equal to b plus m a. Well, the point is this right here is equal to a plus b now as integers mod m. But a plus b mod m, a plus b is the same number as b plus a mod m. But b plus a mod m is the same thing as the addition b plus sub m a. So this is a really sketchy proof, but the point here is that all of these properties come from the fact that addition on the integers has all these properties. And then you just take mod m's. So if two numbers are the same in the integers, they're going to be the same when you take mod m. No, we are not assuming that a plus b is less than m. In fact, that's definitely not the case. Like if I'm working mod 11, I can ask what is 10 plus 10 sub m, right? Here, 10 plus 10 is greater than 11, and the answer isn't 20. The answer is 20 mod 11, which is equal to 9. This is addition modulo m. So obviously not the same addition as the integers, but it comes from addition mod the integers, or addition in the integers. Then you have to remember that you're always taking mod so that you always land back inside the set where you want to be. I would argue that it's something bigger than that. We're actually producing a new, it's called a group. Actually, it's called a ring. So Z is a ring, which is a set with plus and times and a bunch of compatibilities like identity, additive, distributive, etc. And what I've now done is I've produced a new ring with a new set, the set 0 up to m minus 1, with a new addition and a new multiplication that satisfy all the compatibilities. It's true that this in some way comes from this group, and that's very important to remember, but I would argue that this is a kind of important new notion that we won't get much time to explore in this class, unfortunately. But you'll do a lot of this if you do an algebra class. Okay, I've gone like way over now. So hope y'all have a, yes, abstract algebra. I hope y'all have a wonderful Wednesday, and I'll make the homework due on Monday instead. And also everyone should vote and get flu shots. Hope y'all have a great day.